we were looking at the frequency domain characteristics or frequency in view of the duobinary signal, right? So we observe that there is a delay element whose frequency response is denoted by e to the power minus j 2 pi f into dB, right? And there is a direct channel which takes the input signal as it is. It provides that to the summing block. So that has a characteristic of 1. So since there is a sum happening inside the block, we are going to denote that total response of the complete block or the summer block as 1 plus e to the power minus a 2 pi f into t. Okay, that's right. So that's the first part, right? And since this block is followed by what is called as the ideal channel denoted by hc of f, we can take the total response in the following format because, right, on the frequency domain, it is a product, right? So we call it as equation number 1. But now we try to substitute the various values known to us, right? So ideal channel has, right, the following frequency response that you can see on this graph. Whenever the frequency is between minus b naught to plus b naught, we say that it's 1, otherwise it is 0, right? So this particular equation you can try to substitute in the h of f part. Okay, so because there is a product, right? So this becomes whenever the frequency is magnitude of the frequency is outside b naught, the whole h of f becomes 0 because hc of f is 0. All right, so let's try to write that. So this is what we call as equation number 2, right? So we substitute equation 2 in equation 1 to get the following. All right, so this implies what happens to the h of f. H of f is equal to whenever the frequency is lesser than b naught, magnitude of the frequency is less than b naught. This is h of f, hc of f is 1. So 1 into anything is the same thing. So I am retaining 1 plus e to the power minus j 2 pi frequency into dB, right? This is this into 1. Okay, so this is when magnitude of the frequency is lesser than or even up to the equal to, I will include this, it is lesser than this, in a sense within the band. And since whenever the magnitude of f is greater than the b naught, the hc is 0. So 0 into that term, it leads 0 forms. Okay, so we have one standard equation that is taken from the trigonometry. Okay, so that is, if you have an equation something like 1 plus e to the power minus j into 2 theta. If you see something like this can be replaced by 2 times e to the power minus j theta into cos theta. Okay, so this is one very standard identity, right? So that means I can put this back over there so that this becomes equal to, this means the h of f overall transfer function becomes 1 plus e to the power minus j 2 theta. I can see that theta is equal to pi into f into tb, correct? So let's try to replace that, right? So this is equal to 2 times e to the power minus j. I should not write 2 theta, just write a theta. Theta is equal to pi into f into tb. Multiply this with the cosine value, so cos of pi f t. Okay, that's the substitution for the first line. So this is when magnitude of f is lesser than or equal to the bandwidth, right? This is going to be 0 otherwise, or I can still write f greater than b naught. Okay, now normally you see whenever we try to plot the Fourier transform, if you remember, we cannot plot the Fourier transform as it is directly. You cannot plot. Can you tell me what is the reason? For example, I have a signal x of t. I take its Fourier representation, right? That is f. I get x of f. Okay, very straightforward. You use some equation to calculate this. But we don't plot x of f as it is. It's not possible. Okay, can you tell me a reason, or you can guess? Okay. The direct plot is not possible. You have to make some modifications over there, right? So the question is, why do you do the modifications? Why not directly you can plot? For most of the functions, the x of t will be real, but what is x of f? You recall the maybe the most easier way to understand this would be recalling the DFT, discrete Fourier transform in from DSP, right? Your sequence is real. You just write 1, 2, 3, 4. But when you take the TFT is in some format, it is the Fourier transform, correct? So now you tell me what happens when you take the say 4-point DFT of a sequence, right? X of n, which is real, right? What do you get? X of k, right? What's the characteristic? Is it real? No, it is complex, right? So that's the point. I was expecting the same answer, right? Whenever you have a x of t, some of the signals will definitely give you, right, a real x of f, which can be plotted. But in general, right, general case, any general x of t, if you take, its Fourier transform is always complex. All right. Now you see, right, that can be observed from my equation. Just now we wrote some equation, right? Just observe here. Is it real or complex? It's complex because of we have e to the power minus j something. So whenever I multiply by that, it's going to be a complex answer, right? So can you plot a complex number on, if I say uh, my sequence is a complex number, can you plot it? Or what is the way to plot that? Let's assume that I want to plot it. I have a complex that just recall what we did in the DFT. I obtained 8-point DFT of a sequence, which turned out to be a series of complex numbers. But still, you plotted that somehow. Yeah, yeah. How? Uh, Constellation. Okay. Let's. That's actually the omega n part. If I'm right, right? That's a twiddle factor. What you are trying to plot on a circle, right? So that's a twiddle factor. But my question is about a DFT. I had 8 numbers which I got after finding the DFT, and I uh, most of the 8 points were complex numbers. Okay, but you try to plot it somehow. You did something, right, and you try to plot that, and you had an answer. Yes, we can plot it, but not directly this Fourier representation, not the DFT numbers directly cannot be plotted because they are complex in nature, right? So my question is that if you are able to recall, please try to recall what you did. How did you plot? Because normally we have one question that we set in the standard question paper saying that, okay, find the 8-point DFT of the given sequence and plot it. It's a common question. Okay, so there is a plotting part, right? Just to check that whether people know that we cannot directly plot it and we want to do something so that we can plot it. What is that? See, butterfly is actually the FFT, fast Fourier. Again, the answer is once again DFT, right? The name fast Fourier comes because the calculation is faster. That's all. Okay, but the answer is once again DFT only. You get complex numbers as the answer at the end of butterfly diagram. You give input on the left hand side, right side you get the answers which are once again complex. So my question is that those numbers which you get as answer, right? I want you to plot them, right? So it's about plotting, not about the calculation of the DFT or FFT, right? So I'll come to the answer directly. Okay, so we have two options, right? If this h of f, right, it is actually a complex, right? So if I want to visualize this, I have two options. One is if you have alpha plus or minus j beta, this kind of representation, all the numbers you separate alpha, right? Everywhere, every number. If I have four numbers like 2 plus j3, 3 minus j4, 8 minus j9, 3 plus j7, right? What I do, I separate all the real numbers and I plot in one graph. One graph is called as real of your function. The second one is imaginary of the same function. Like I this is now j axis. So j3 minus j4 minus j9 plus j7. You see, it's actually, I don't have any other option because 2 plus j3 cannot be pointed out on a single visit. Okay. So that's the reason you have one option by that is to plot by using the real of your number, real of your whatever h of f, and separating another plot for imaginary of the h of f, for which you need to plot. This notation is not capable of doing that because this is not in the a plus jb form. Correct? This is in some other form. Right, so let me tell you that. So this is complex. So if it is present in alpha plus or minus j beta format, then the plot will be real. One plot will be real plot. So the first plot that we are going to write will be the real values. We try to plot only alpha. So real, I write a real plot, followed by I write the imaginary. Correct? If you remember, this is what we do. If at all it is present in the required format, that is first format, it is alpha plus or minus beta. So what do you call this kind of representation? It is called as rectangular. Correct? It's a rectangular notation, alpha and j beta. Right? There is another format that is called as the polar. What is a polar format notation? Recall, it is r into e to the power, you can have plus or minus j theta, right? I'll write simply, right? Plus or minus j theta, e to the power. So where r is the magnitude and theta becomes the phase. So what you plot here, first plot will be magnitude and the second plot will be the phase, right? So I'll write in bracket what you plot. For the first one, the real plot is alpha and imaginary plot is the plot of beta values. At the same time, if you have r into e to the power plus or minus j theta, right? The magnitude plot includes only r. I plot just r, and the phase plot will be the phase, the plot of plus or minus theta according to the given equation, right? According to the representation. So polar format will generate something like this. Right, now you see, I'll come back. So why I told, because I need to know what I am plotting and why I am plotting. So you see h of f, which is definitely complex. Now you should be able to identify that my function, right, is in this format. It's r into e to the power plus or minus j theta, where r is this part, this is the r, right? And e to the power, whatever you have, it is the e to the power plus or minus j theta format. Are you okay? So because of that reason, now if you want to visualize this particular h of f, if I, in a sense, if I want to plot this, right, I have to separate the magnitude and the phase. All right, so that's the reason why I took so much time to explain this. So separating the magnitude and the phase of h of f. So let us try to separate now. So that means when I separate this, first thing is magnitude of h of f denoted in this. So that will be equal to, so it is 2 times. Now the magnitude means you neglect the even the negative numbers, right? If you have a negative number, that becomes positive. So right, I apply the magnitude to the cos function because cos can take negative value, correct? So cos of pi f tb, right? This is the only magnitude when the magnitude of f is lesser than or equal to b naught. This is going to be 0 if the magnitude of f is greater than b naught. All right, so let us try to look at this waveform, right? This is just a magnitude plot. Okay, so this is f. So this is what I'm trying to plot as magnitude of h of f. Now you put f equal to 0 because the horizontal axis is f, right? When you put f over there, when you put f equal to 0, this is cos 0. Cos 0 is 1. I need to multiply that with the 2. Multiply that by 2. So 2 into 1, when frequency is 0, this is the highest value, that is equal to 2. Okay. Now, when you put f equal to b naught, okay, f is equal to, I'll try to put b naught over there, right? Whenever I put b naught, so immediately after b naught, this is going to be 0. So that means after b naught, this has to be 0. So this has to start from here, it has to come down and reach here. Similarly, on the other side, I have minus b naught, right? So it also has to reach the 0 by the time it reaches 0. Are you okay? So this is the frequency's magnitude response of the frequency. At different frequencies, I get something like this. At the same time, now let me go for the phase. Phase is denoted by theta of f, right? At what frequency, what is the theta value, right? You see here, I need to identify the theta by looking at this. So if you remove the j from your equation, whatever remains is the theta. So theta is equal to minus pi f t. Okay, so it's j theta, whatever is there with j, it is the theta. So this means it is simply minus of pi into f into tb. Again, the same conditions will be applied whenever the magnitude of f is lesser than or equal to b naught. This is equal to 0 when the magnitude of f is greater than b naught. Now you see f is a frequency. Okay, so f is my variable. So left hand side, take the theta of f. Theta of f is, I call it as y. Okay, f is my input, so I'll call it as x. The minus pi and tb, whatever you see, right, it is a constant, correct? Because for a given system, the bit duration is constant, tb is a constant, pi is 3.14. only it is negative. So you see it is something like y is equal to minus m into x. Are you okay? This equation, theta of f is equal to minus pi f tv, I'm going to say that it's a straight line. Are you okay with that? Yes, right? Now, if the slope is positive, this means the straight line will look like this. It's increasing, right? Sorry. If the m is negative from the basics, we know that that particular straight line will be a decreasing function, right? Again, from the basics, right? So you see this here, the slope is negative, so this is a decreasing function. That's what is my conclusion. But also I will understand that if you see there is, whenever you write y is equal to mx plus c, this c denotes the y-intercept, correct? If c is present, the straight line cuts y-axis at some point. Where it is going to cut, you will identify that. But now you see y is 0 here. I don't see, sorry, the c is 0 here. I don't have, right, the c value. It's simply y equal to mx. I know that y equal to mx passes through origin. So it is a decreasing function, first point. And the second point is that it passes through origin. So two things I understood. All right. So let's try to plot this directly. So just to identify the characteristic of what we are trying to plot, I took this much time. All right. So let's directly try to plot. So this particular uh, graph is for the theta of f. So let us say this is minus b naught. Somewhere here, I would like to say that is a plus b. All right. So when I put the b naught value over there, so at minus b naught, right? Whenever I put this is minus b naught. So f is negative. Already it is negative. Minus of minus, it becomes positive. Okay. So and the b naught, whenever I put here minus b naught, right? The b naught is equal to, right? It's actually the half of your total TB. This is the TB, right? It's half of that. So it actually becomes minus pi by 2. Sorry, minus of minus plus pi by 2. So if I call this is plus pi by 2, I'll write this is minus pi by 2. So you see that its response will be something like this point to this point. It's a straight line. I already have taken care of that. So it actually starts from this point, passes through origin and reaches the other point. Okay, so this is the phase response of uh, the h of f, whatever we can. Okay, now we can also try to write a time domain equation. That if you want to get a time domain equation, what you do, you already are in the frequency domain, right? You have to come back to the time domain by taking the inverse Fourier transform. All right. So let's try to write an equation. This is the frequency domain view, whatever we were considering so far, right? So we got two things to learn. First thing is how to obtain the magnitude response. That's what you see here. How to write the phase response, theta of f. Okay. Now, so now we can write the impulse response, right? Therefore, the impulse response equal to, right? You take the inverse Fourier transform of the h of f, right? So impulse response is denoted by h of t. Impulse response is the response in time domain. So the frequency response is called as the Fourier transform of h of t. But now I don't have h of t, now I have h of f. So if you want to calculate h of t from h of f, you have to take what is called as the inverse representation. So general equation is this is minus infinity 2 plus infinity, the h of f into e to the power plus j 2 pi f into t into df. You see, integration happens on the frequency domain. That's why it is df. Okay, so this is equal to, let's try to substitute. Anyway, I know that my signal is not existing from minus infinity to plus infinity, but it actually exists only between, right? It exists between minus b naught to plus b naught. All right. So into h of f is already known, that is 1 plus e to the power minus j 2 pi into f times tb, right, into e to the power, this is j 2 pi f t into df. Okay, so when you integrate this, let's try to do integration, right? So that means I will first multiply, that is integral minus b naught to plus b naught. This is e to the power j 2 pi f t plus e to the power, I'll take a j 2 pi f outside. So this becomes t minus t. Okay, so this is simply t minus t. Okay, this whole thing with the df. Okay, now let us try to substitute. So when you integrate this with respect to f now, not t, what happens? It is e to the power j 2 pi f t divided by j 2 pi t. Okay, substitution happens between from minus b naught to plus b, plus once again this is e to the power j 2 pi f into t minus tb divided by, it is j 2 pi into t minus tb. Okay, once again substitute minus b naught to plus b. Right, now that means I have to write in the following fashion. This is e to the power j 2 pi, okay, I'll take the okay, divide by the common number, that's fine. So e to the power j 2 pi b naught into t minus e to the power j minus j 2 pi b naught into t, all divided by j 2 pi t. That's the first term, right? Reduction of the first term. Then write the second term. This is also, this can be written as e to the power j 2 pi b naught into t minus tb by first term minus e to the power minus j e to the power minus j into 2 pi b naught into t minus tb, right, minus tb, whole divided by, this is j 2 pi times t minus tb. Okay, now, so can you further reduce? Can you suggest something? Right? Can you use any of the trigonometric identity to substitute over here? So there is e to the power j theta, right? And minus e to the power minus j theta. You can see that, right? So can you do something with this? Sorry, can you repeat? ht uh, from mathematics, right? You're taking that from maths. Yeah. That's right. That's right. So we can actually bring the sign into picture. Yeah, right? So that means, okay, let me write it this way. So it's e to the j theta minus e to the minus j theta by 2j, right? Is nothing but the sine function. It's a sine theta, right? I can see a 2j over there, correct? Right. So when I see a 2j over there, I can definitely substitute in this way. Or I can e to the j theta by e to the minus j theta by 2j. Okay, let's try to substitute. So this is equal to this. I can simply write this. It is sine of j theta is there, right? So I can write a sine of 2 pi b naught t divided by 2j has gone, so you will have only pi t. Okay, that's the first term. Plus second term is once again sine of 2 pi b naught times t minus tb whole divided by j2 pi, j into 2 has gone out. It's just pi of t minus tb. Okay, I somehow got a sine function. But if you are able to bring a sine theta by theta, this becomes a sinc function, right? Which is more standard, because sine of 2 pi b naught t by pi t, no, I don't understand. I don't know how this looks like. But if at all I see a sinc function, I know initially there is a bigger lobe. As time progresses, it reduces, correct? So just to bring that, what you do, you substitute the b naught value. So actually the b naught is nothing but 1 divided by 2 times the TB, correct? Because 1 by TB is the total frequency, half of that is B naught, correct? So you see B naught is here and the B naught is here. So this 1 B naught, sorry, this is minus B naught. From 0, 1 B naught is half of that. That's why it is 1 by 2 times TB, TB in the denominator, okay? So let us try to substitute that, so that we can understand what exactly is this particular waveform is going to look like. That's h of t. Still, I have h of t on the left hand side. So that implies h of t is equal to substitute. So that is sine of 2 pi into, there is a b naught, correct? So b naught, I know that this is 1 divided by 2 times tb into t whole divided by pi times t, correct? So 2 and this 2 cancels. Okay, let's try to bring the simplification later. So plus, once again, I have sine of, this is 2 pi into b naught is equal to 1 by 2 times tb into, this is t minus tb whole divided by, this is pi times t minus tb. Okay, now, so if you want to bring the sinc function, it is sine theta by theta. So what I do, anyway, it's cancelled. Sine theta is equal to, there is a pi, I have a pi, I have a t, but I don't have tb in the denominator, correct? So what you do, so for this whole function, you multiply and divide it by tb. There is a tb in the numerator, there is a tb in the denominator. Okay, right. So that means this, the numerator of the numerator tb will come into the denominator as divided by tb, because denominator of the denominator goes to the numerator, isn't it? Right? So that tb I can write in the denominator, which makes this as sine theta pi into t by tb divided by pi into t by tb. So that means it is a sinc function. Okay, same thing happens with this. The same tb I can bring into the denominator, pi times t minus tb divided by tb, so that you can see the same thing inside the sine theta function. Sine theta is equal to pi into t minus tb by capital T. Okay. So I can call this also as a sinc function now. So both of them are the sinc functions. Okay, so the sinc function directly I can write. So there is a 1 by tb outside. Let's try to write that over there. So this is 1 by tb times, this is sinc of, what's the function? Okay, there is another notation. If you can take the pi outside, you can write whatever is remaining, I can write that. So right, but for that the tb should get cancelled. Anyway, let's write it in this way. So the denominator tb and the numerator tb, whatever you have written, okay, or there is another version to write this. I think that is much easier. Okay, instead of don't multiply and divide by, this is more easier. Okay, so there is a standard notation, right? Sine of, if you have something like pi, right, you see that pi tb by t by something, only this term can be substituted, this term can be retained, right? So this can be simply written, right, sinc of t by t, standard function, plus the second function can also be written as sinc of, see the t minus tb by tb, because right, you can see that the t minus tb and tb in the denominator, the two anyway they get cancelled, but the condition is that denominator should be, right, this the pi into the numerator part, that's already there, right? So I don't have to multiply actually. All right, it's a standard function, so simply you can recall. So this is the h of t, right? The impulse response is going to look like this. So let's directly plot this. So the general waveform will look like this. So this is h of t. Now we see there is a small difference, right? I have to mark 0 tb. It is not a simple function, simple sinc function. It is a sum of the sinc, right? So it's 2 tb. This is 3 tb, and so on. I'll write another one, 4 tb. On the other side also, I'll write few of the values, minus tb. This is minus 2 tb. Maybe I'll write one more, minus 3 tb. Now you see the sinc function actually, right? If you consider only the sinc function, sinc of t by tb, that is actually having a maximum value here, right? Reaches the 0 here, right? And so on. Is it okay? This is what is the waveform for the first one, that is sinc of t by tb. I hope you are okay with that, right? This is the, I just write in dotted line because this is not the final answer, right? Now I'll change the color. I'll go for a different one, that is sinc of t minus tb by tb, right? I'll try to plot this in this way. So t minus tb means what? It is actually shifted to right, because there is a minus, t minus tb. If I write x of t minus t naught, that is the right shift. So it is right shifted by how much? Right shifted by tb unit. So the same waveform you can see coming like this. Okay, so something like this. Now you see, fundamentally you are adding both of them. Are you okay? So that means I'm supposed to get this waveform. Now I'm trying to club them. Okay, I'll try to highlight. So something like this. Okay, it may not be a very big, but you see, this is how it's going to look like. Right, now you see, actually what happened, we had one pulse over here, that pulse got overlapped with my next pulse. This is what our fundamental concept we studied at the beginning today, right? I added two pulses. I considered two consecutive pulses, 1 and 1. Right? So you see, this is what you receive at the end. As an impulse response of your filter, you have the same response, correct? Coming at the output. So whatever we assumed initially, because I told that, okay, we'll assume something, right? Whatever we assumed earlier, now we have proved that. I hope this is clear, right? Just try to remember what we did. I'll just show you. Any doubt you have, let me know. Otherwise, I will proceed. Okay, so starting from here, the frequency domain rule. I'll start from here. Just go through this. I'll keep going. And any doubt, at any point you have any doubt, please let me know. Stop and will explain. Otherwise, we'll proceed further. Yeah. No, it actually depends on what I plot. I plotted this is bigger, right? Right, but it's something like you may have, right? Normally you see exactly what happens. I'll tell you. I'll try to plot it more clearly so that it becomes more clear to you. Okay, now you see, for this given the black colored dotted line, see this is bigger, okay, and this is smaller. Actually that's what is happening, right? I'll just erase this part, because the first uh, crest or the trough will be larger. Okay, the first one is larger, then it keeps on reducing. All right, so just remember. Okay, now for the second graph, that is a blue colored one. Now you see this is actually larger, because that's the first crest, right? So actually that is bigger, so that's why this is coming lower, right? The red colored is below. Same thing happens on the other side. I didn't make I just plotted a rough estimate over there, but you follow this means you get, right, the same red color which we have plotted. Okay. So the first one is more deep, then the next one is slightly lesser, then lesser, and so on both the sides. Same thing is has to be repeated for black dotted graph as well as the blue dotted. Okay, once you satisfy that, definitely the red color which we see will come into picture. Is it okay? All right. So again, this is now time versus the h of t, time versus magnitude. All right. So we have another question now, right? Okay. So far we discussed that. Okay, there is a concept called correlative coding, right? How to build the correlative coders we understood, right? We saw a block diagram, called it as a duobinary signaling. Everything is absolutely fine. What if there is what if there is an error made by the receiver, right? We saw that. So far everything looks very fine for us, but practical scenario is always different. Okay, so there is a problem in this kind of technique, that is a duobinary signaling, normal duobinary signal. That's what we uh, we were studying so far. In that we have a problem. Okay, that is called as the error propagation, right? One of the drawback, error propagation in the duobinary signaling scheme. Right. Let us try to understand what is this error propagation, uh, right, by default. Right. Let's try to see. Okay, let's try to see the error. All right. That is, let's take the same old, I can save some time, but if I consider the same old system, okay, let me just copy this. Okay, some of the lines were not copied. Anyway, it doesn't matter. I don't want the last few lines. So let me fill this. Once again, BK was there. Then below that we have the polar, right? So if you remember, this is -1, -1, +1, +1, -1, -1, -1, 1. So anyway, we obtain the CK in the same format like we did earlier. So -2, 0, 2, 0, 0, 0, -2, 0. Okay, that's what is a CK. Now let's go for the BK. Okay, BK cap is equal to, it's the equation says it is CK minus BK cap -1. Right. So now you see there is an error. Instead of assuming the -1, let's say we add a +1. Right? This is an error. I'm inducing error because I just want to show that what happens. So this is the error. We induced an error. Okay. Now you do the calculation. What's going to happen? I'm just going to add those two. So this is -2, -1. So you see this is completely out. This becomes -3, right? Then 0 minus -3 becomes +3, right? It's not just one bit which goes into error, right? It completely propagates, right? So that is done. So 0 minus 3, then +2 -3, this is -1. 0 minus 1 is -1 is +1, 0 this is -1, 0 this is +1, -2 -1 is -3, 0 -3 is +3, and so on. You get some, right, newer values also coming into picture. So this is what is called as the error propagation. So the fundamental idea is that as far as there is no error, this is absolutely fine. Okay, so we didn't observe the error and the related concepts because the channel we assumed was ideal, right? Initially, we made a comment that, okay, we are assuming the ideal channel, right? But ideal channel is not going to work, right? Always, right? We will never see the ideal channel. Always what we get is called as the practical channel, which will definitely bring the concept of error. There will be error, and that error will, if you don't make the certain required modifications in your modeling scheme, that is a duobinary scheme, always there will be what is called as error. Okay, so that's the concept, right? So that concept is we need to modify something now, right? So slightly we have to make the modifications in the uh, incoming, sorry, in the duobinary, the block diagram which we had written earlier. We have to make the modifications in that so that even if there is an error, right, it will not propagate. See, the point is that you can never avoid the errors. Errors will definitely happen. That's the nature of the channel, right? Communication channel will definitely introduce error, right? So on the receiver side, you have two options. The first option is that you try to rectify the error, right? For rectifying the error, you should know how to detect the error, correct? So makes sense, right? Only when you detect an error, okay, my fourth bit is error. When I detect that this fourth bit is in error, then only you can do something to rectify, correct? So error detection is important. So first aspect is that practical issue, right? So how do you rectify? So rectification comes into picture by uh, at an additional cost. You have to have a circuit to perform that, right? I understand that, okay, there is an error. What could be the correct bit over there? You have to, so if it is just 0 or 1, you don't have to worry, because 0 is an error, means change it to 1, it's fine. Okay, but normally you don't have such simple system, right? Because for most commonly you have say 16 bit QAM, 4 QAM, or something like that. You see M array system, right? There are M number of symbols sent, not just 0 and 1. So one of the symbol is error, means it could be any of the remaining 15 symbols, right? So it's not easy to replace that error symbol by something else. Okay, so as I told, you have an option like, okay, you have to have a error detecting circuit for sure, but will you go for the rectification circuit, error correcting circuit? Will you go for that? That's a question. If you say yes, it comes at an additional cost. In the sense, maybe the receiver design becomes pretty complicated, right? Components are not simple, so you have to have very complicated internal blocks also, which are costly, increases your cost, increase the complexity, power requirement, and so on. Many things will come into picture. So that kind of design is complex. That's all. But anyway, so those who want, definitely they'll go for it, because right, cost is not an issue when the efficiency matters. Okay, right. Otherwise, there is another option, right? I don't want to make my receiver circuit complicated, but still I use first part, that is error detection. Error detection will take place. Okay, but what you do, you don't rectify it by yourself. Simply ask the transmitter, make another communication with the transmitter, ask that I lost your fourth bit, send again. Okay, simple. So because transmitter knows what it has sent, right? So it can look at, maybe it's a table, or maybe it's a list or array or something, right? Go to the fourth position, take it and send it, right? So another version, so simpler, but it actually takes some time, right? In the sense, so in the middle, whenever the request goes from the receiver to the transmitter saying that I need this fourth bit, there is an acknowledgement signal coming from the transmitter to the receiver. You see, you lose your actual communication, which is supposed to happen. In the middle, it breaks down. So there are, you have to balance which one you want to use. Okay, will you go for the first one where the circuit is complex? Otherwise, you go for the second one, which reduces your speed of communication. Right, there is a trade-off, right? You have to choose an appropriate one so that you can proceed further. All right. So anyway, that circuit design, etc., is not included in this kind particular syllabus for sure. Okay. So in this particular topic, that's duobinary signaling, the upcoming topic will be modification of our circuit so that error will not propagate. There will be error, but the error remains only in that position. It will not propagate. Okay, we can definitely make that modification. That's what is going to come in the next class.